Hey, good evening. This is Mr. Murray coming to you with a little video on dilations. Wasn't really requested, but I thought that I would make a little video just to help you understand some of the problems that we encounter when we're doing dilations. So I thought I'd start off with a little definition, and to kind of motivate this, what I have here is where some of you might have seen dilation in your real life, dilated pupils. So maybe if you go to the eye doctor, right, you get a little drop in your eye. And what that does is it causes your pupils to dilate. And notice how here and here we have a circle. The center is exactly the same, right? So what's happening is that pupil, right, this black part of your eye, it's coming out in every single direction by the exact same amount. See, it still retains its circular shape, but now it's a much more pronounced. It's much more, the radius is much larger, okay? So that's a sense of dilating, taking all the points and moving them up, stretching them out by the exact same amount. So it's fair to say stretching as opposed to moving them up, okay? And it all emanates from a center point, so it's the dead middle of your eye, okay? Right, and so in class, we've seen dilations, more with like polygons. So here's a triangle that's been dilated by a certain scale factor, and when that happens, right, it's obviously a scale factor more than 1 because we're producing a much larger triangle, okay? The shape stays the same, right? It's still a triangle. The ratios between the sides, so like the ratio of this side to this side is equal to the ratio of this side to this side, so those ratios stay the same, but now the new shape is much larger, okay? In coordinate notation, what this would look like, and this is not all the time, when we're doing a stretch, maybe if it's from the origin or shrink, that's when we'd see it, okay? And this xy is indicating that it's going to, the x is going to be multiplied by a number, and the b is going to be, and the y rather is going to be multiplied by a number, okay? And so multiplying the x and the y coordinates, usually almost always when we're on the origin being our center of dilation, that's how you know you're going to see a dilation. So when things are being multiplied, okay? And so we define dilation as a transformation that takes each point of an object, whether that be a polygon, multi-sided shape, polyhedron, a multi-faced shape, and scales that point by a given scale factor. So it's all stretched by a set fixed number called the scale factor, okay? We consider the dilation to be a non-rigid transformation because the corresponding parts of the image and pre-image, right, in other words, this image being the pre-image in this case and this being the image, do not retain their distance from one another after the transformation is performed, right? So with a rigid motion, this is a rigid motion. If I take this little triangle and I move it over, and it becomes this little triangle, okay? So this is just a rough sketch, but you can see each point, any 2 points, right, in the image are the same distance away from the corresponding points. Rather, any points in the pre-image are the same distance away from the corresponding points in the image. So, right, we have this point, and their corresponding points are this point and this point. The distance, more or less, and you have to forgive my diagram here, is more or less the same, okay? Whereas here, if I pick 2 corresponding points, and I'll just do this easier, I'll just choose the vertices, okay? These points are not the same distance away because this point is farther from this point than this point is from this point, right? So the corresponding parts in the pre-image and the image no longer maintain their proportionality, the same distance. They're proportional, but they're not the same, okay? So that's what we think about when we talk about dilation. So I thought I'd put this little explanation of them on there, okay? And if you need to rewind and have me go through that, I encourage you to do so. But then I'm going to jump into some of the nuances behind dilations. All right, so dilations are what I would call maybe not explosive. They're an explosive transformation, okay? Because when you have a dilation with a given center point, I said this in class, it's almost like this is like an explosion, and everything blows out from this point right here, right? And I think if you look at it that way, like everything's, you know, blowing out, expanding out from this center point, right? It will help you understand which way the shape is going, right? So it's important that if this is blowing up, this shape, this point is going further. It's going out this way. This point is going back that way. This point is going back that way. That's important, okay? But it really depends where it is. And I apologize for my spelling. I'll fix this one. Okay? So when it's in, notice how now the center point of the dilation is in the middle of the shape. So now it's pushing this point up this way, this point out that way, and this point back this way. So it has a little bit different effect. Instead of pushing everything back, in this case, they're being pushed in different directions, okay? And finally, in this last explosive transformation, you can see that, well, if this thing, everything explodes out from here, this point's going to get pushed this way, this point this way, and this point this way right here. So what this I'm trying to get at is the location of the center of dilation matters, because that tells you, one, which way the dilation is going to be moving as it dilates out. So is the dilation going to be pushed going, you know, kind of towards the right or towards the left? And then it also gives you a sense of where everything is centered at, because we're going to see that's one method for doing these things, okay? So there's 4 main methods for dilations, and to help us understand this, what I did is I broke it down using this flowchart. I like to think about it as all around the center of dilation. So where are we dilating from? If it's from the origin, that's the easiest case in my opinion, because all we're going to do is we're going to take all the coordinates, we're going to multiply by the scale factor, and that's going to push everything out, and we're kind of done. So the origin's the easiest case, okay? And this is what I would call, what I'm getting at, right, our 4 methods. This would be method 1. This is the lowest energy method. If we have the origin as our center of dilation, rock on, dilate it out. But what if it's not the origin? What if it's another point? So if it's close to the origin, one method you could use is you could translate all the points. So the center of dilation, so let's say this is my point. This is pretty close to the origin. What I could do is I could translate this back to the origin and apply the same translation to each of the original points. So it's back to the center. I could do my dilation, and then I could translate back and undo the original translation. So you translate it so the center of dilation's on the origin. You pretend like it was the origin the whole time. You go back and use this method, method 1. You get your answer, and then you push it back however much you moved it, the opposite of what you moved it to start with. And we could take a look at that for sure. But if it's not, if that center of dilation is not really near the origin, well, I would say, is it easy to calculate the slope between the center and the vertices? If it is, you could use the slope method, okay? So if this is my center of rotation, this is a point that needs to be dilated. Actually, let me get a whole triangle in here, okay? So here's the point I'm going to dilate. Well, if I need to go up 1 or over 2 and up 1 to get to this point, and the scale factor is 3, well, then I'm going to have to go over 1, up 1, over, or rather over 2, up 1, over 2, up 1 twice. So now I'm 3 total distances of over 2 and up 1 from where I started, and that becomes the new point, the slopes method. Finally, the last method is I call the will be method, after the person who was the first to really vocalize this. And that is where you redefine. So now you pretend like this is the center, though it's not really, it's the origin. Rather, I guess the origin. You go back, you do method 1, keeping all points relative to here. So if this was like -1, -1, but really with this as the origin, it would be quote unquote 1, 1. You do it with that 1, 1 notation, like as your coordinates. You do the dilation, and then you re-express the final point, remembering that this is the actual origin. So that's the will be method, redefining the origin as the point of dilation, the center of dilation, doing your dilation, and then switching back. And we'll see both these methods. The translate, dilate, translate method, or what I guess I've abbreviated as TDT, For a lot of people, that's actually, they say, oh, it's too much work. And so if that's you, I'm not locking these other methods out. Feel free to use whichever one of these, we have 2, we have 3, and we have 4. Feel free to use whichever one of these you want. When the point is not the origin. They're all going to get you the right answer. It's just a matter of what are you comfortable with and what's going to be, the most work and the most realistic for you to execute. Okay? So I'm going to give you an example. This is an I do problem. So we'll have some I do problems, some we do problems, and some you do problems in this video. Okay? So I need to dilate this shape given that the center of dilation is 0, 0, and the scale factor is 1.5. So when you're given a center of dilation, I always recommend you're going to go ahead and label that center of dilation. Now, what's good about this is it's 0, 0, so that's actually setting us up for a good deal. So originally, let's lay out our points. I've got original A is 4, 3. Original B is 2, 4. Original C is -4, -2. And original D is 2, -2. So now I need to do a scale factor of 1.5. Okay, so ordinarily I would need to, and you could look at it with slopes 2. Think about this. Ordinarily I'd have to go over 2 and up 4 to get from the origin, the center of dilation, to B. So I'm going to have to go up by 1.5 that much, right? So it would be like multiplying. So maybe I'll make some space here so we can see our primes. Okay. All right, so what we're going to do in this case is, since it's the origin, we're going to multiply each of the coordinates by 1.5 because that's the scale factor. So here's A. So now A prime is going to be, well, -1.5 times -4, that's -6. 3 times 1.5, that's 4.5. Okay, so let's put that on there. -4, -5, -6. 1, 2, I guess it should be 4. Let's try that again. So if that was 4, that would be +6. I miscounted. So that's -4, 4. So sorry, it should be -6. 1, 2, 3, 4, 5, 6. Okay. B, 2, 4. So B prime, well, 1.5 times 2 is 3. 1.5 times 4 is 6. So we have 3, 1, 2, 3, 4, 5, 6. Okay. Now notice if I do my slopes up to, so there's 2 of these up to's. So 2 times 1.5 is 3. So 1, 2, 3. Here I'm going up 2 over 1, up 2 over 1. So it's 2 up 2 over 1s. So then I'm going to go 1, 2, 3 of them. Okay. Now, what about -4, -2? That's going to go to -6 because 1.5 times this. -3, 1.5 times that. 1, 2, 3. Notice that you have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9. So now, because of the scale factor of 1.5, this length from new A to new C is 1.5 times as long as this length right there. So you have that notion of proportionality. And then finally, D, which is 2, -2, it's going to give me a D prime of 3, -3. Again, the same method of multiplication. And what I get is this brand new dilated object right here. A prime, B prime, C prime, D prime. And technically, this really should be C and this should really be D. But I think what's most important right now is that you are able to actually do the dilations. You know, I'm probably going to get comments like, Mr. Murray, shouldn't this be C and this be D? Yes, technically true. But I'm going to focus right now on the dilations. I appreciate you saying that. Okay? All right. Sorry, I lost that one. Where are we? All right. So, there we go. So, here we go. I'm going to go ahead and ask you if you need to. Please take a second and erase and kind of go back, adjust anything you need. Make sure you understand where I'm coming from here. and then in a moment I'll move on to the next one. All right, so now another I'm going to dilate DEF, given a center of dilation of -2, 1, and a scale factor of 3. So here's -2, 1, and I'm actually going to call an audible on this. I'm going to actually make it -2, -1, because that's kind of on the line. I'm going to do -2, -1. And my scale factor is 3. So now notice the point of dilation is located inside. So think about this. This is going to be our explosion. So it's going to go, it's going to push E out. It's going to push F down. It's going to push D down. Okay? So let's look at the slope. To get to E, I've got to go over 1 and up 3. Scale factor of 3. So I've got to go over. So now I've got to get 3 times as far. So look, this point is 3 up 1 over 3s, right? 1, 2, 3. This one is only one of them. So therefore, what that tells me is that I've gone 3 times as far to get to that new point. Okay? Here's the other way we could do it. Actually, I just want to finish out this way, and then I'll show you the other way we can do it. I like the will be method. So here's our point again. So to get to F, down 1 over 3. So I need to go down 1 over 3, down 1 over 3. So now I'm 1, 2, right? 1, 2, 3, down 1 over 3 is over. And now finally, and remember, you're not going up this way, you're going down this way. This is the little explosion center, so it's going to push D out this way. So 1, 2, 3. Okay? And now I've got my brand new point. Some good signs. D and F are still on the same horizontal line. So that's maintained. But now the figure is blown way out. Okay? I'm going to show you the will be method on this I try because I think it's worth talking about. So what I'm going to do is this. I'm going to plot, maybe let's make this blue. And I'm going to pretend that this is the new center. So ooh, I do not like that line at all. So I'm going to pretend like this is the origin. Okay? Bear with me on this. So this is the origin. Forget this 0, 0. So E is technically, put that in quotes, in this coordinate system, it is 1, 3. Now, it's not really, right? 1, 3 we know is really over here. But relative to this center of dilation, it's over 1 and up 3 from that one. Okay? F, in quotes, is going to be 1, 2, 3, 3, -1, because it is 3 units to the right and 1 unit down. Okay? And finally, D is -2, -1. 2 units over and 1 unit down. Now we apply the scale factor. Okay? So E prime, we're going to multiply by 3. So that would give me 3, 9. But 3, 9, if I look at this as my center, is 1, 2, 3, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, relative to that point. F prime, in quotes, is 9, -3. Again, the same method, multiplying each coordinate, but now 9, well, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 2, 3. Right? And I should be at 7. 1, 2, 3, 4, 5, 6, 7. And then finally, D rather, prime, is -6, -3. Because if we're on the origin, then it's just as easy as scaling the individual coordinates, right? So 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 1, 2, 3. Okay, relatively speaking. And now what I can do if I do light pencil, erase the little coordinate grid that I made here, and I can connect a brand new scaled triangle. Okay, notice we have a length of 1, 2, 3, 4, 5, and then a length of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So this is a length of 5, this is a length of 15, right? You can see the sides have been scaled. This is down 4 over 2. This is down 4 over 2, down 4 over 2, down 4 over 2. It's a factor of 3, okay? All right, so again, go through. Please make sure you understand what I just did here, and then in a moment, I will move on, and there'll be one for us to try together. All right, rock on. We're going to the next one. Dilating. So here's one for us to do. We need to dilate JKL, given a center of dilation being -2, -6, and a scale factor of 1/2. So what's the first thing we need to do right now to set this up? We need to plot our -2, -6. So -2, 1, 2, 3, 4, 5, 6. Here's our center of our explosion. So here's what I know. I know that, and I know my scale factors. Think about it. Everything's going to blow. Well, in this case, the scale factor is 1/2. So everything's going to pull in. This is an implosion. But if it's 1/2, everything's shrinking in towards this point, being sucked back in. Okay? So let's think about this. I'm going to do the will be method. So remember, we make this, pretend this is our origin. Okay? So here's what I want to know. Let's take a look at this. So we have J in quotes, K in quotes, and L in quotes, right? They're not the real JKL, but we're got to get them relative to this point. So take a second and think about it. What is J if this was 0, 0? How would we write J in this new coordinate system? We would write it as -1, -1, -2, -3, -4. How do we write K? K would be 0, or rather 1, 2, 3, 4, 5, comma, 0 in this new system. And L would be 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So it would be 6, -6. Now we apply our scale factor. So we have J prime, supposedly, would be -1/2, -2. K prime would be -2.5, 0. 0 is nice and easy to multiply. And L prime, in quotes, would be 3, -3. So we come back up, and now where are we going to plot it? Is it going to be starting with here's the origin for these 3 points? No, it's all relative to here. So -1/2, -2. I'm going to plot this in blue. Okay? K is going to be -2.5, and actually this should be not -2.5, +2.5, because that's a 5. So 1, 2, 2.5, 0. And then finally, 1, 2, 3, -1, 2, 3. Here's my brand new points. So J prime, K prime, L prime. Drop that original. If you do dotted lines, get rid of them in the end because they're going to be really confusing. And here we go. Now, in the end, if I ask you to state your points, it is good to be able to get back to reality and state my points. So the real J prime in the actual coordinate system is 1, 2, 3, 1, 2, 3, 4. So it's actually, no, it's actually -2.5, 4. K prime is actually -1, negative 1/2, 1, 2, 3, 4, 5, 6. So it's 1/2, 6. And L is really 1, 3. L prime. Okay? So make sure you know this. All right, so hopefully this made sense. Again, if you're stuck, please go back and take a look through. But then in a moment, we will move on to another problem for us to do. All right, wow, here we go. This is going to be one for you to try, okay? So I have MNO. I need to dilate it. It's got a center of dilation of 1, 2. Scale factor of 2. Okay? I want you to go ahead. I want you to try on your own to do this dilation. Okay, so we're going to pause the video. We're going to try to do the dilation, and then in a minute, we're going to unpause, and I will show you how to do the dilation. All right, so remember where we're going to start. We're going to start by hiding our important info. So the 1, 2, and the 2. So remember, identify my center of dilation, my scale factor of 2. Okay? Now, we need to dilate. So here we go. N is 1 unit away from 1, 2. So it's going to be moved to 2 units away, right? The explosion is going to come out this way. Okay? It's an explosion because it's more than 2. Or rather, this is more than 1. Okay? M is 1, 2, 3, 4, 5 away. So I have to move it another 1, 2, 3, 4, 5. 1, 2, 3, 4, 5 away. So now M used to be 1, 2, 3, 4, 5 away. Now it's 10 away from the point of dilation. O is the trickiest one. So O, to get there, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. So I have to go down another 1, 2, 3, 4, 5, 6, and over 1, 2, 3, 4, 5. And this will be 6. Okay, so here's my brand new shape. Okay, not the best out there for sure. You guys will probably do better with your pen and paper, but this is what we're going to want to do. So we have this point, so we have M prime, and that goes to negative 9, not negative 9, 0, negative 9, 2. And I kind of did use that method, right, where I pretend this was 0, 0. I used a little bit of slope method in my head, so I did a lot of things there. Okay, N prime, that is negative 1, negative 1, 2. And O goes to 1, 2, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it was 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. Okay, so we actually need to fix that. 1, 2, 3, 4, 5. No, it is 6 away. So you need to go 6 more. That gets me to negative 11. And then I need to go down 1, 2, 3, 4, 5, 6. So I'm at negative 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. So that would be negative 10. Okay. So again, what did I do? I basically used my slopes to figure out how far each one away was, and then I doubled it using the scale factor. So this one was only over 1, so it doubles to over 2. This one was over 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it doubles to being over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This one was down 6 over 6, so I had to go another down 6 over 6. So now it's 2 of those away from the point. Okay, you could have redefined this as 0, 0 and done it that way too, and hopefully you got the same thing as me. All right, so again, please make sure you understood what I did here. Make sure you agree that I've got N prime here, M prime here, O prime here, and then in a moment I will move on to the last problem. Alrighty, so here we go, the last you try. So now I've got PQR with a center of dilation 0, -3, and a scale factor of 1.5. I'm going to again ask you to pause the video. Do your best to solve the problem on your own with graph paper if needed. And then in a second, unpause and I'll show you how to solve it. All right, so here's what we got. I'm going to put my center of dilation, remembering my scale factor of 1.5. So here I'm going to pretend I'm going to use my slope. So I've got to go up 1, 2, 3, 4, 5 to get here. So I've got to go up 1. So this is 5, right? And you know what I'm going to do just to make this even easier, because I've got a really nasty scale factor? Let's use the will be method. Okay, so Q in this method is 1, 2, 3, 4, 5. It's like it's 0, 5. It's not really, but if this was the origin, then relatively speaking, yes. P in this new system is 1, 2, 3, 4, 1, 2, 3, 4. I just want to double check that. 1, 2, 3, 4, 1, 2, 3, 4. So P is -4, -4. R is 1, 2, 3, 4, -4, -2 in our new system. So now to get our primes, supposedly Q prime, well, 1.5 times 0, 1.5 times 5. Okay, P prime in quotes would be, well, and remember P would be above, so it's a +4, -4, +4. So 1.5 times -4 is -6. 1.5 times 4 is 6. And then finally, R prime supposedly is -4 times 2, -2 times 2. Okay, so let's plot it. So now, relatively speaking, new Q prime, I start here with my 0, 0, 0, 1, 2, 3, 4, 5, 6, 7.5. Okay, P, -6, 1, 2, 3, 4, 5, 6, up 6, 1, 2, 3, 4, 5, 6. And then R, -6, -3, 1, 2, 3, 4, 5, 6, 1, 2, 3. Okay? Now delete all my new axes so that's not confusing anyone. Whoop. And then I will connect. So I've got to connect these. Got to connect these. Got to connect these. Okay? So this is my new Q prime, my new P prime, new R prime. So it's been blown back. And notice if I have to go up 0, up 5 and over 0, I've got to go here up 7.5. Here, notice the slope was, in this case, left 4, up 4. Well, now I'm going left 6, up 6. Okay, so it's 1.5 times each of those directions. So again, the final P prime, though, in terms of this is the actual origin. It would be 1, 2, 3, 4, 5, 6, -6, 3. Real R prime would be -6, 1, 2, 3, 4, 5, 6. -6, -6. And real Q would be, or rather real Q prime would be 0 and 1, 2, 3, 4, 4.5. Okay? So dilations aren't easy, but I hope in this video what you've seen is that it's really, really important to read your problems thoroughly, to understand where the center of dilation is, and then based on that to take a valid strategy using the scale factor, whether it be redefining, well, first of all, it's the center, just scaling it, or redefining the center, scaling it around that fake center, right, like I did here, or using the slopes to effectively make your shape larger or smaller. Okay, hope you found this video helpful. Keep at it with the math. Be sure to check out my other videos, and hopefully there'll be more of these to come. But remember what I always say, you can do it. All right, thanks again for watching. Don't forget to love math and have a wonderful day.